This is discussed in detail by Henderson and Liu, 2019, Cognitive Load and Decision-Making in Expert Contexts, Journal of Applied Cognitive Psychology, Volume 33, Number 4, pages 287 to 312. To a reader, this looks like an authoritative source. The formatting is precise, the journal is a real publication, and the volume and page numbers fit the standard academic style. But when you try to look it up, the trail goes cold. Volume 33 exists, but there is no paper by Henderson and Liu in that issue. In fact, that specific paper doesn't exist at all. Every name, date, and page number was generated through the same predictive process the model uses to write a simple greeting. This fabricated citation reveals a gap in the technology. It can produce text that is stylistically perfect while being factually empty. To understand why AI generates these phantoms, we have to look at what it was actually trained to do. To understand this behavior, we have to look past the interface. These models do not function like a search engine or a database of facts. They are built for one specific task: next token prediction. This is the mathematical objective the system was optimized for during its entire training. The model sees text as a series of fragments called tokens. Given the sequence, "the cat sat on the system calculates the most statistically probable next token. In this case, it predicts Matt. Throughout its training, the system is rewarded for making these predictions match the text it was shown. Truthfulness and accuracy are not part of the signal it receives. Plausibility is. Through trillions of examples, the model learns the patterns of human language, how arguments unfold, how citations are formatted, and how experts sound. It treats the grammar of a fact and the structure of a lie as identical patterns. Within the logic of the prediction objective, a fluent truth and a fluent fabrication look the same. The model has no internal sensor to tell the difference. There is no "I don't know" option in the training. Even when information is missing, the instruction remains the same: produce the most probable next token given the context. While we read for meaning, the engine is optimizing for the statistical shape of a sentence. We can apply these rules to the Henderson and Liu citation to see how the prediction objective builds a fabrication token by token. When the prompt asks for a source, the model predicts that an author name should come next. Henderson and Liu are plausible names in this context, so they score a high probability and are selected. The previous tokens now narrow the mathematical possibilities for the next one. A recent plausible year, 2019, is the next statistical step. The topic requested in the prompt guides the engine to string together academic keywords, forming a title that sounds like it belongs in the field. Finally, it adds a real journal name and plausible page numbers. Each piece was the most likely next token, but at no point did the model verify if the paper actually exists. This wasn't a malfunction. The system was executing its primary directive, prediction, flawlessly. These hallucinations are not bugs to be patched. They are a feature of a machine designed to mimic the patterns of human fluency. The prediction objective works so well because it targets a specific human vulnerability. We often use style as a proxy for substance. In most contexts, when we encounter confident, grammatically perfect text, we assume it is backed by actual knowledge. This creates the danger of answer-shaped text. These are outputs that provide the structure of an answer: the claims, the tone, and the justifications, without any underlying truth. When we treat a fluency engine as an oracle, we are misinterpreting the tool. This technology is highly effective for drafting, summarizing, and pattern generation, tasks where the goal is a plausible structure, not factual retrieval. But the model itself is isolated. It doesn't track whether its output is true or false, because those concepts aren't part of its objective.